we will begin our session. It is SPE and OSA student chapter. The first speaker will be Sir Michael Berry, United Kingdom, Nature's Optics and Our Understanding of Light.
Well, good afternoon to all of you, and thank you very much for coming on such a nice day when you could be enjoying the sunshine. This talk is very kindly supported by the Optical Society of America, and they have asked me to show a very short presentation about their organization. So here they are. This is the Optical Society of America, and they're a professional society for scientists who are interested in light in many different aspects: industrial, conceptual, theoretical, and so on. And they are a worldwide organization. They have members in many countries and organizations in many countries, and 18,000 members, and student chapters, of which you are one, in many parts of the world, 85 in Europe. And they provide support for students, so if you need support, it's good to contact them to see if they can help you. And there are a number of benefits, different programs. If you look online, you can find out everything about it. Good. So now we come to the lecture. I have to quit from this program. Open another one, if I can find it. Here we are. For many years, in my talks on optics, I have enjoyed using natural phenomena that one can see with one's own eyes to illustrate different aspects of optics. Now, the optics of nature is a much studied subject. There are many papers about it and there are many books. And this talk will not be a standard presentation. Over the years, I've accumulated a number of insights which until recently I did not publish. But now I have gathered them together and made a talk about insights of different types about optical phenomena in nature. I did not write this talk until very recently. Now the subjects I'm going to speak about are actually published. Why now? Because this is the International Year of Light, and this lecture is my way of celebrating that event. It's also something else. I want to pay my respects to Marcel Minnaert. He was an astronomer who specialized in optics of nature many years ago, 100 years ago. And he wrote a very influential book, The Nature of Light and Color in the Open Air, which in a way began the serious study of the subject I'm going to speak about. Many aspects had been studied before, but his book was a defining moment. It has been reprinted many times, including by the Dover Publishing House, who should be ashamed of themselves because they printed the colours of the rainbow in the wrong order. Okay. Can you understand me? Yes? Thank you. Very good. So let's begin. The first of my examples is the rainbow. And I want to emphasize two features of its understanding. Now, here is a rainbow, and I want to point out that you see two rainbows there. Here is one, and here is a second. I will not be speaking about the second. Now, it was understood for a long time, many centuries ago, particularly Roger Bacon, that the rainbow is a phenomenon to do with sunlight and droplets of water, sunshine on a dripping cloud. But the theory of the rainbow, why there is a bright line in the sky, was not made until 1637, and by the philosopher René Descartes. And he realized that what the rainbow is a focusing phenomenon. The word for focusing, a place where focusing occurs, is a caustic. Caustic comes from the Greek word for burning, and if you take a magnifying glass and you wish to make a fire on a sunny day, then of course you can use it as a lens and you can focus and you get burning. That's the origin of the name. But he realized that this focusing occurs with light emerging from a raindrop. The light comes in uniformly distributed, but it comes out focused in a cone. It's a cone because you have to rotate about this line, because it's a sphere and not a disk, of course. Now, each raindrop emits a bright cone of light, focused light, and you, on the ground, looking up, see brightly lit all the raindrops on whose cones your eye is situated. And you have to think about the geometry, but that's a line in the sky. Now, Descartes had to use the law of refraction. We call it Snell's law. He called it Descartes' law. It was known before by Thomas Harriot and many centuries before by Ibn Zal in Baghdad. But the law of refraction, the way in which light bends when entering a medium with a different refractive index. And he used this to calculate the deflection, here it is, as a function of the place where the ray is incident. And he saw that the curve has a fold in it. Here it is, it has this fold, and that means that light coming in that particular place emerges concentrated, and that's the focusing. Now, nowadays, we do the trigonometry. It's not very difficult, and we have a formula for the rainbow angle in terms of the refractive index, and the refractive index is n as a formula. Now, Descartes did not have this formula available to him. It's the minimum deviation. He needed calculus, but calculus was not invented then. So he did exactly what we do now when we find mathematics too difficult for us, which is usually the case, I should say. He did a numerical experiment. So this might be one of the first numerical experiments in science. He calculated in a graphical way the points I've shown you here, and he saw that you have this minimum. So this was a numerical experiment. Now, some years after Descartes and Newton, of course Newton explained the colours because the refraction is slightly different for different colours, and so the rainbow angle is slightly different. He did this. But shortly afterwards, people began to notice something strange. Look here. You can see a small additional ring in here, an additional line. And these were called supernumerary rainbows. This means unwanted, unexplained. People didn't like them. And it was a long time before, almost a century, before Thomas Young realized that what you are seeing here is a wave effect. You're seeing something beyond the ray description. You're seeing that light is waves, and these are actually interference fringes between the two rays that emerge from a raindrop at angles away from the rainbow angle. Now, this is an interesting picture. I'm showing you this particular picture because it shows you something that Isaac Newton was not able to understand, but this house is the house where Isaac Newton was born. It's very unusual to see a rainbow in a particular place. Okay, so here, very often, depending on the distribution of sizes of raindrops, you see a large number of fringes. Here is an example. I've never myself seen so many as this, but you can very often see 2 or 3 of them. Okay. Now, of course, if you have a wave, you have a wave function. You have to describe it. So this was a problem that Thomas Young announced, and it was 30 years before George Airy, the astronomer royal, there he is, before he actually understood the wave function that describes the intensity across a rainbow as the function of this variable z. Now, he realized he was doing fundamental physics. He was not simply describing one phenomenon, although it's important to do so. He was realizing that he was describing wave physics near the singularities of geometrical ray physics, the old theory. Describing the decoration of how waves decorate caustics in optics. And he had a function. It's an integral. Okay. It depends on this variable z. Here it is. Now, here's a picture of it, and the square of it gives the intensity. Now, Airy had the same problem as Descartes. He was not able to calculate his, this function. He could calculate, with a clever method, numerical, only this little range. Now, so he also did a numerical experiment, just like Descartes. And this was very frustrating because people had measured a number of these oscillations in the laboratory, 30 of them actually, in the experiments with glass spheres filled with water. So it was a very difficult situation. One had a theory, but one was not able to calculate what one wanted to calculate. Well, this was achieved 10 years later by Stokes, who realized that in order to understand the decay on the dark side of the rainbow and the fringes on the bright side, you need asymptotics. You need to study this function when z is much greater than 1 or much less than 1. So here is Stokes, and he found approximations to the Airy function. Here they are. On the dark side, this decay faster than exponential. On the bright side, these oscillations. Now, this already was a great achievement, and anyone should be proud of it. But Stokes was a much deeper thinker, and he realized there was something rather strange about these formulae, because here is one mathematical function, the Airy function. But on one side, you have an exponential, one of them. On the other side, the cosine, you can write it as 2 exponentials. So how could the same function be 1 exponential on one side and 2 on the other? If you transfer this exponential from x to minus x, you get one of these two, but where's the other one come from? And he realized that it comes from something very deep. These approximations are the first terms of mathematical series in powers of the reciprocal of z. However, they are divergent series. They look as though they converge, they're useful for calculation. These are just the first term, but then they diverge. And he realized that the appearance of this small exponential is intimately connected with this divergence. Now, this is mathematics which is too difficult for me to describe now, but I will say that this work of Stokes, which came from the rainbow, is at the very heart of our understanding now of these divergent series, which appear everywhere in science. It's very rare to get a convergent series such as you learn in school. You learn about infinite series and when they converge, but the ones we meet in science usually don't. And this is a very active area of research even now. So, finish with the rainbow, numerical experiments of 2 kinds, and the beginning of our modern understanding of divergent series. Right, now we come to the sparkling of light on the sea. I'm speaking about this. Now, you know that these images of the sun are on places where the slope of the water is exactly correct to reflect light into one's eye. If the water were perfectly flat, then you would just see one image of the sun. It would be a perfect mirror, but it isn't. Mathematically, it's a many-to-one map from the sun to the eye via the water. This was studied a lot in the 1950s, but there is something about it which is still unsolved, and this is what I want to draw attention to you now. Many pictures, it's very easy to create these pictures. Sometimes there are huge numbers of thousands, millions of brilliant points, depending on the conditions of the water and where the sun is. Now, as time passes, the water is waving, and these images move. they come together in pairs and disappear, or they are born in pairs. Now what is happening then? In the space above the water, the sunlight is focused onto caustic surfaces, like this. And these events occur, I've just drawn an instant there, they occur when one of these caustics crosses the eye, because these caustics describe regions reached by different numbers of reflected rays. If your eye is here, you see one image. If it's here, you see 3. If it's here, you see 5. And these events, which are called twinkles, and indeed the twinkling of the stars is a similar phenomenon, because the atmosphere is irregular and focuses the light, and when caustics cross your eye, you see multiple, well, you don't see because they're too small to see, but what is happening to give you the changes of intensity is that images of the star refracted by the atmosphere coalesce and appear or disappear. Now here's the unsolved problem. Sometimes when a brilliant point, an image is born, it dies with the same image it was born with. Other times it dies by colliding with a different one. Now this phenomenon of colliding with the same one and disappearing, I call it lifelong fidelity, being faithful to your partner your entire life. You're born together and you die together. Now the question is, what fraction of these images has this property? And it's a rather difficult problem. It depends on the statistics of the water waves. I will just illustrate this in one dimension. Imagine the eye is fixed, and here is a space-time diagram of the history of images when you have a random wave but moving rigidly, just moving rigidly. Well, here you see 2 are born. This one, if one annihilates here with a different one, a different one, a different one, there is no lifelong fidelity. Here are 2 interfering waves, 2 waveforms traveling in opposite directions. And here, most of the images have this property. You see this one is born, 2 are born here, and they die together. Born and die together, born and die together. Not all of them, but some of them. Now, with even the simplest statistical model of the randomness on the water, we don't know how to calculate what fraction of images has this property. So I just tell you it's an unsolved problem. Good. Third thing, mirages and green flashes. Okay, light bent and dispersed by air. Actually, the green flashes comes a little later, never mind. Excuse me. You've all seen these mirage images on a sunny day when the road is perfectly dry, but it looks as though it's wet, and it looks as though you're seeing the images of distant cars reflected as in a mirror. Here you are. It's a very common phenomenon. Now, it's known that this is total reflection from the hot air very near the ground. Hot air means less dense. More dense as you go up. Rays are bent towards the denser medium, that's refraction. So here's an object, and here you see it directly, but also you see it by this refraction. Now let's look in more detail. The rays bend towards the denser medium, that's the air above. Okay. Now in more detail, if you have a smooth refractive index, locally it's varying linearly, and here it is. I just want to make a remark that this simple picture of geometrical optics was not understood by one of the greatest optical scientists, a man called Raman, C.V. Raman, a very great optical scientist, and he wrote a paper claiming that this explanation was impossible and you need another one, and so on. He was wrong, but he was non-trivially wrong in a way that I didn't understand until last year. I wrote a paper about it, but we won't discuss it. Now, here's the point. A point on an object does not emit a single ray. It emits a family of rays traveling in all directions. And families of rays have a property, holistic, which individual rays do not have. They can form these caustics. They can focus. No one ray can form a focus. You need a family for that. Okay, it's the envelope, mathematically, of the family. And I won't go into the mathematics, but for example, here is the family coming from a point source, a point on the object, let us say. Well, you can calculate, here it is. So here's the object, and here's a local approximation to these caustics. It's a paraboloid, it's in 3 dimensions. Now, you may have seen the upside down version of this picture, because it's the most elementary calculation in military science. If you have a gun which can fire projectiles with a given speed, but in any direction, what is the region that can be reached? Well, each orbit is a parabola, and the envelope of all the parabolas is a paraboloid. It's called the bounding paraboloid in artillery. So it's this is the same thing in light, but upside down. Now, an object isn't a single point, it's a collection of points. So we have a family of rays. And here the caustic is important in understanding what happens. You see, here's the picture I showed you. Now, if the point you are looking at has a caustic which is below your eye, as here, then you see 2 reflected images. One is upright, one is inverted. If your eye is below, if it's here, then you don't see any mirage reflections. So the caustic is the boundary, it's called the vanishing line. The caustic is marks the points on the scene which you can, below which you can observe the mirage reflected and above which you can't. So these are the points whose caustic passes through your eye. Okay. Now, you can make more realistic models of the refractive index. It doesn't just need to be linear. Of course, it goes from some value near the ground up to the normal refractive index of air above. Here's a little exponential model, the details don't matter of that, but you can calculate the rays exactly for this model, and here's the picture you get. Now, as I've been showing you, you get no images below the ground, and then you get 2 images of this one point, but here you only have 1 image. Why? Because those rays would actually hit the ground. So this boundary is just an ordinary shadow. Now that's not everything, and this now comes the point I want to make. Sometimes you see more than 2 images. Here's an example where instead of hot ground, you have a wall heated by the sun. So the mirage is horizontal rays, and the displacement is horizontal. So here you see distant image of people standing, and in fact you see 3 images. Now I've spoken about 2 or 0 or 1 if there's a shadow. Now why is that? Well, there are several reasons why this could happen, but one of them is this. If you have a maximum refractive index, and the situations can sometimes be quite complicated near the ground. For example, if you have a refractive index like this, as above the ground or sideways from the wall, which is more common, then you can get continual focusing and defocusing. In fact, the rays are like this from a point. So that means you can see many different numbers of images, any number you like. So this is one mechanism for seeing more than 1 images, more than 1 image. Okay, now we have something else. So, excuse me. I just wanted to point out that for the last 3 examples, we've seen the central role played by these caustics, these focal domains, and they're the singularities of ray optics, of geometrical optics. But now I want to go on to something else. Sometimes the things one sees arise because of coincidences. The most familiar one is this. The moon and the sun look almost exactly the same size in the sky. The sun is much bigger, but it's much farther away, and by coincidence this exactly compensates. And this is why during an eclipse of the sun you can see this beautiful phenomenon. The moon obscures the sun, but only just, so you can see the beautiful atmosphere of the sun, the corona, outside. Well, I'm going to tell you about a different coincidence, which I discovered many years ago, but I didn't write about it until now. It's this. There are 2 circumstances where you can see light from the Earth on the moon. One of them is at new moon. The dark side of the moon is facing us. There it is. Here's the sunlight and here's the